undo the share, a bunch of things happened, but this time it decided to work. So no issues there this time. Now we've got a half a minute, so we'll just hang on for a moment. If you have any questions, don't hesitate to ask them. And we'll usually start right on the minute, unless there's a question. About the longest 15 seconds ever, but I think we're about there. Welcome back, everyone. So we have a slight change in the roster, so I thought probably the best thing we should do is just run through the Moodle website once more, just to kind of orient ourselves, especially since day one, we put out a lot of information. It's hard to catch everything. So on the main Moodle website, the general tab is where I try to collect a lot of resources. I'm going to try to utilize the announcements form here. It sends out a message whenever I use it. Looks like I haven't used it just yet. Then we've got the standard things like the syllabus. If I make any changes on a document, I try to indicate by putting a revision and a date. So if you printed it out, you'll know there's been a revision after the printing. And I did make a revision on this, so let's take a look at it. What I changed was, well, I put here revised. My revisions are in red, and I put a Tuesday here to add an extra day in the middle of the week. And I want to also, I emphasized if I thought it should be just written in, it makes more sense. Half the class is in person and half the class comes in from remotely. When I'm in room 220, and this is just on Thursdays, I'll also be available in Zoom. I just thought I should write that into the syllabus to be specific about it. I use the same exact Zoom link for really all my classes and office hours. It's this one right here. Now, if the weather gets just really unmanageable, even for folks who come in person, you are welcome to use this. There's never a good idea to drive through hellacious conditions just to make it to class. So that's the changes on the actual syllabus itself. These office hours down here are pretty special, like we mentioned. This is in this math center, the student success center, you might call it, in room 220 in the Idaho Falls campus. But the math center is closed this week. So what I'm going to do this upcoming Thursday is, well, 220 is locked. I'm just going to be in tab 268. So if you wanted to see me physically for office hours, that's where I'm going to be just this next Thursday before they open up that tutoring room. Or you can come in through Zoom, like we mentioned. Any questions about those things so far, folks? Okay, then let's go through here. This is just a document to say which calculators are allowed on exams. We'll discuss that much again as a reminder when we're getting close to one. Our Zoom link's here, and all the recordings for the class is going to end up here. If there's some weird technical glitch and the recording is just gone beyond repair, then we might lose one, but that's very, very rare for these classes. So if you click on recorded lectures, we have our first one right here. I try to indicate the section 5.1. I try to indicate the coverage, and sometimes I have to correct things. That should have said 2.2 for that right there, but we'll get a correction put in a moment. After that is our WebAssign. This is where our homework is going to be administered. And I updated this document right here. Someone in class, I forgot exactly who it was, but thanks goes out to that person. There's a weird little thing you can toggle. When you go down to this step, registering, you can select multi-term access. It drops the price down to $72.15, and you're not actually losing any content. I think that might be a potential pricing bug on WebAssign side, but I'd say get it for the cheapest price possible. That's always the best advice. You're not losing out by selecting multi-term access. That just sounds like more access. Any questions about that, folks, with registering in WebAssign? Okay, close that for a moment. And after that, if you have issues, technical support is right here. They have a number and a chat system, but I have another offer. If you do have issues, you can also email me, and I can work with the technical support on your behalf. So if you have something strange happening in WebAssign, and just decide you don't want to deal with those folks, get in contact with me and we'll work it out some way, somehow. This is here just for really a class tool for calculators. And this one, I think we looked at it a little bit in class. This is the Discord server. Let's take another close look at this. On the Discord server here, everything is completely optional. I'm new to Discord, and some people might be new as well or much better at it than I am. But its purpose is it's completely for students and only for really study groups and homework help. You could completely ignore this Discord server entirely and be okay in this class. What you'd probably do if you're using it is go down to Survey of Calculus, and you could just post a question and get answers from fellow students in this class. In fact, let's do that right now just to show what it could look like. Let me go into WebAssign. Okay, so logging into WebAssign, the student view would look about like this. And if you asked me a question and I responded, you'll see something like that, a little text box that says there's a response to one of your questions. Let me click on that. You'll see the response right here. And this is the kind of stuff I usually write out. I try to give indications of what to do next or advice on how to run through the problem, that kind of stuff. And if the information I need to put right here just doesn't work, maybe I need to write down a mathematical symbol, I'll probably just email you directly. So you might want to have your ISU email open as well, just to make sure you catch that message there. I would put here, I emailed you a response to this question, check your email if I need to write out math symbols. Well, let's put down, just to show how the Discord might work, you could do this on the Discord server. Anything in red means these numbers change on a student by student basis, but the structure of the problem is the same. It's really the same question. You might have a 2 there, a 3 there, and a 5 there, but the whole problem is the same. If you're working on a Windows machine, you could use the snipping tool, and the shortcut is hit the Windows key, the Shift key, and the S key simultaneously. This new screen pops up at the top, and your cursor turns into a plus symbol. Just crop out the portion where your question is. There we go. Then in the Discord server, you can hit Control V and just directly paste it in, type out a message and say, hey, anyone see how to start this one? And that's one way you might interact with the Discord server. A lot of different ways you can do it, and anyone in the class is welcome to post questions and post answers and those kinds of things. And it's a way you can do kind of a rudimentary study group. If you want to up the ante and make the study group even better, you can coordinate with people in the class and go down to Survey of Calculus. This is a voice channel here. You can do voice, screen sharing, and all sorts of things for a real honest study group using this platform. Well, any questions or comments about the Discord server? Okay, like I mentioned, if you don't like Discord, no worries. I'm trying it out for the very first time this semester, and it is weird. I can see how it's possibly helpful, but if you decide it's just not for you, that's okay. You can get direct homework help always from me by directly emailing me, visiting me during office hours, and that's a fine way to get help as well. Down below is just some optional reading. All the lecture notes are blanked out here because these ones, after we work on them, we'll post the solutions. Even if we haven't completed the notes, we'll post the partial solutions as well. So that's the structure of the Moodle website. Any questions or comments at all, folks, so far? Okay, well, if you have other questions, don't hesitate to ask. I'll talk a little bit more about WebAssign, in particular things like what to do if something goes past due. Keep in mind, just as a reminder, there are due dates, but these due dates are really for the purpose of pacing. If you complete this assignment by Wednesday, January 17th, 7 p.m. is just the start date of our class. The date, the time is not meant to be any big deal there. Complete it by that time and you're in great shape. If life gets a little bit busy, you can always request an extension. You don't get penalized, but it does mean you're catching up at that point with the course. So you're working a little bit harder than really intended. But I encourage everyone, use this button as needed. There's never a penalty. we'll look at that more when assignment goes past due on just what it looks like in the system. I think that's pretty much the announcements I wanted to put out today before we got started. Any questions at all so far, folks? Okay, well, the other announcements I had put here are that we're on example 2. And next Monday, we're already on holiday. We've been working hard, so we're going to take off Martin Luther King Jr. holiday and meet again next week after today. Let me close us off, and looks like we're ready to begin. But first, any last questions, comments, concerns, or worries, things like that folks would like to get out there before we begin? Okay, as we start this off on the lecture, folks, and coming in through Zoom, you're completely welcome to participate using voice. If you're in a noisy environment or you just rather not to, you can also use this chat as well. And one thing that's a little bit weird about that is my chat is a continuous chat. This is just the last class, so ignore everything there past this point. I'll put maybe new class just as a indication. Oh, I'm trying to send to Alex. I should be sending to everyone. Try again. Well, that's not working. Well, I probably won't respond in chat, so it's less an issue on my part, but that's weird. I'm not sure how to change who I'm trying to talk to on this. But if you decide to use a chat, then these things are kind of easy for me to miss. They don't pop out too nicely. So if you in class, whether in Zoom or in person, if you notice a new chat goes through and I missed it, it's never going to be rude to say, hey, Mike, you missed a chat, and I'll get right on it. That's never a rude thing to do. Sometimes getting through these kinds of classes is a bit of a group effort with all the weird technology we're running. So that's our announcements, and here's where we left off last class. We're on example 2. We're taking the limits of a function, but maybe just to kind of warm ourselves up a bit, let's take a look at first, after I get my windows in the right spot, what we did right above here as a reminder. The limiting process is an algebraic process truly, but it's really great to learn it first as a geographical, in the terms of geometry. What does the actual geometry of a limit look like through these graphs? So on this horizontal asymptote, y equals 2, when we took the limit as x goes towards negative infinity, got to select the right one, it means we're looking at the long end-term behavior of the graph as we go far to the left. The red curve seems to be settling down at a height of positive 2. We wrote the limit of that function as x goes to the left forever, settles down to around 2. It may not hit it exactly, well, it's going up and above it, but that's where it's getting closer and closer to. Towards the right, it's getting closer and closer to positive 1, so we indicate that there. It's not a coincidence that these are also the horizontal asymptotes in the problem as well. So visually, this is what limits at infinity look like. Then what we've tried out next is doing it without the aid of a graph. We're going to try doing this algebraically through the limit laws next. First problem we did was really just a warm-up. It was 1 over root x, so we converted this to x to the power 1/2. Once we exhibited the actual exponent there, we observed that for any positive exponent p, the limit of 1 over x to the power of p is equal to 0. Let me try to clean that up just a little bit. So we use limit law 8 to get through that problem, and this one is a pretty big superstar. We'll try it out again in part B. Well, before we get too far, let me take these laws. I'll just use this as a screenshot and walk it along the problem as we go to the next ones. That way we're not scrolling up and down a whole bunch just to look up a limit law. So here's our next one, part B. And it definitely looks way worse, right? Oh, geez, let me try to keep those there. Part A just had one thing we had to work out, and now we're dealing with an entire rational function. Now, if you know information about rational functions, you might be able to solve this problem in one step exactly. Because recall, there's a theorem here that says, if you have a horizontal asymptote, you have found the limit. So looking at this problem here, anyone happen to know what the horizontal asymptote would be for this as a rational function? 5x minus 9 divided by 3 minus 7x. definitely is a random question. If we're not sure, no worries. There's another way to do this. The process goes like this. Let's actually write this out. To solve this limit, select the value. Let's, instead of saying value, let's make this a little bit more descriptive. Select the term in the denominator I'll put here just in the parentheses without the coefficient. So we'll select the term in the denominator with the highest power. So looking in our denominator, this is always going to be the process. Here, the power of x is 0. This is really 3 times x power 0, simplifying to a 3. Here, the power of x is 1. So this is the power, or excuse me, this is the term with the highest power. We don't want the coefficient -7. It's unhelpful to work with it. We're going to work with that x. We'll say next here, divide all terms by this term. So if this x that's circled here by the red dot was power 3, we're going to divide all terms, numerator and denominator, by x cubed. It's just x, so we're dividing everything by just x in this problem. So here's where the problem starts. It goes, it equals the limit as x goes off to infinity. We're dividing everything by x. So in the numerator, it'll be 5x. Divide by x, minus 9 divided by x. It's looking ugly. It gets kind of hairy before it cleans up, but we're on our way. Here, divide by x as well. So it's 3 over x minus 7x over x. Now, if you did this in your head, the simplification, and just gave me 5 minus 9 over x, that's completely fine. I had a little bit of steps, extra steps in the actual notes, just for a paper trail, so you'll know how I got to this step right here. So on the next one, it's going to be limit. X is going off to positive infinity. Here we're just simplifying. So 5 minus 9 over x divided by 3 over x minus 7. So after simplifying the term here and the term here, this is what we're looking at. And now we need to take the limit of this thing. The limit laws are here for us to help us. And a lot of these things we almost just take for granted. For example, if we look at this limit law, number 6, it says if you're taking the limit of a fraction, well, you can just take the fraction that involves the limit of the numerator and the limit of the denominator. We don't always write in that step, but what it's telling us is this limit operator is affecting both the numerator and the denominator simultaneously. And it's okay to take for granted that it affects both at the same time. If we did write in this step right here, it's truly optional. We'll only write it in part B to emphasize it. But this is equal to the limit as x goes to infinity, 5 minus 9 over x. So there's your numerator portion. Divide by the limit as x goes to infinity of 3 over x minus 7. So that's the content of limit law number 6. It says you can take the limit of the numerator denominator independently if this limit exists. Now that we're done that, up here we need the limit of 2 different terms, 5 minus 9x, same in the denominator, but that's what limit laws both 1 and 2 are telling us. If you take the limit of a sum or a difference of functions, the result is the sum of the limits or the difference of the limits. We won't write in that step, but what it's telling us is we're taking the limit of 5 and the limit of 9 divided by x at the same exact time, and that's okay by these limit laws here. Does that make sense to folks so far with the limit laws? Okay, in effect, this is really what's happening. If you like arrows, then this limit operator is distributing here, 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 and here, and you're taking the limit of 4 different things, much like you took the limit of this one thing right here. So that's the idea with the limit law so far. That looks crazy, so let's take that off. That was just for emphasis. And now we need to take the limits of all of this stuff. First, let's focus on the constant 5. We take the limit as x goes to infinity of 5. Well, that's this limit law. Nothing happens. There's no x there. It's a constant. So it doesn't matter what happens to x. These are going to get an output of 5 right exactly here. So no change on that 5. We'll write it in. Next, let's focus on this part of the limit, 9 over x. Notice I skipped the negative. We can write in the negative right there. That's what happened with this negative on the limit laws. So I got 5, the minus, and we focus on this limit right here. But notice, you're really just using limit law h right there. Let me draw it in just for the sake of emphasizing that. We're taking the limit as x goes to infinity, 9 over x. If we want to use limit law number 8, we need to say what the power is on this x. But x is equal to x power 1, so there it is, the power is 1. That power is greater than 0, and so this whole thing is 0 in the limit. It takes quite a while to write that out for something that's just coming out as a 0, and so this is what we typically really do. Up here, we know that's gone, and we might write this out. Goes to 0, just as a reminder. So 0 on there by limit law number 8. Does that make sense to folks so far on the numerator right here? Okay, same idea on this one. We're taking the limit of 3 divided by x this time. It's no different than 9 divided by x. The fact that there's an x in the denominator means, well, if x is getting larger and larger, your 3 over x must be getting smaller and smaller. And there's a fun way to demonstrate this, not even using a graph. Let's open a calculator. Now let's take a really close look at 3 over x. Let's call it a function. F of x equals 3 over x. So we're looking really closely at that function. Now we want to know what happens if x gets really, really large. Let's take first f of maybe 10. That'd be putting 10 in the denominator, and you get a 0.3. If you increase the power, it goes to 0.03. We're up to 10 to the power 3, so 1,000. You're getting a 0.003. But x is not stopping at 1,000 or million, billion, trillion. It's heading off to infinity. It's growing without bound. So up here, we need to put in larger and larger values and just see what happens at every step. The larger the value plug in, the smaller the result. But in the limit, as x goes to infinity, that becomes 0 itself through property number 8. These are just getting smaller and smaller as the input to x gets larger and larger. So we'll go over here in the work and just say, that one also converges to 0. It's gone because of the x that did survive in that denominator. So we now have 0 here. And then back to black, minus 7. We took a problem that was a limit of a function, a complicated looking one. We worked out the limit laws by using the strategy here in orange. And this is what it comes out to. At this stage, we don't write the limit operator because we're done taking the limit. We're just going to write -5/7. And we did it, folks. That's the value of this limit right here. But now coming back to the original question, if the limit exists as you go to infinity, meaning you've got a finite number, that number right there is the horizontal asymptote of that original function. And it's not a coincidence that the 5 here, the -7, is exactly what came up when we took the limit. So we got -5/7 either way we looked at it. This strategy here doesn't always work out. sometimes there could be different powers. Like there's power 1 on top, power 1 on bottom. Whenever there's a tie, this little strategy works out. But the good news is, if you copy this strategy, you have to worry less about what's happening with the asymptotes and more, it's just a process that works, whether it's a rational function or not. Well, questions, folks, on getting through part B? Okay, looking at the homework assignment, this is pretty much the meat and potatoes of the assignment. We're taking limits like this one right here. This is basically part B exactly. And we're going to change them up eventually to different kinds of stuff like what we see here on the problems down below. Any questions at all so far? Well, I think I already asked that, but any come up so far? Okay, let's try out another one just to get that practice in. And here's our next one to give a try. Well, same as before, it's a rational function. The same strategy that we used before, we're going to try to use again once more. Sorry, I have an open mic. Let me fix that real quick. So we look to the denominator of the function, and we're going to pick out the term with the highest power, exclude any coefficients that might be there. To start off the strategy, that means in the denominator, we're very interested in that term, the x power 3. Everything will get divided by it, and that's how we'll kick off the process. After we divide everything by x power 3, we just go to limit law 8 and any other limit laws we need, and we finish off the limit. So in actuality, this is really pretty fast. And if you happen to know the asymptote, you can write the answer in right exactly here. And there would be no judgment. That's good mathematical knowledge, just knowing the asymptote. Well, let's try out the process. And if you know the asymptote, you probably know the answer as well. First thing we're going to do is take limit. Let me try to highlight this a little bit better to show the process. We have to write the limit as x goes to infinity for full credit using limit notation, and then go. I'm first focusing on the numerator, divide everything by x cubed. So x squared plus 4, both of which divide by x cubed. So that finishes off the numerator. Now let's write in the denominator and same thing, divide everything by x cubed. So it was x cubed minus 6x plus 1. But if we divide by x cubed here, here, and here, we'll be able to compute the limit, but more importantly, we've maintained equality because we didn't change anything algebraically. We divide by the same value, numerator and denominator. So that highlighted equality is maintained. After we get to this stage, we just need to simplify all these powers that we see here. So this is the exponent law portion of the problem. It's now limit as x goes to infinity. Over here, x squared over x cubed just turns into a 1 over x. This one doesn't simplify, so we'll leave it in as plus 4 over x cubed. And lots of simplifications down below. That denominator comes in as a 1. Here we get my 6 over x squared. And then here, no simplification, plus 1 over x cubed. Now, everything that has an x in the denominator now goes back to limit law number 8. Again, that's a pretty big workhorse for the limit laws in this particular problem. So on this one, x survives with a positive power. That's power 1 in the denominator. So this one's going to 0. Likewise, so is this. The power is even higher. So it goes to 0 even faster. Negative 6 over x squared is going to 0 as well. And so is 1 over x cubed. So all that stuff is now just gone. And the limit turns into 0 plus 0 divide by 1 minus 0 plus 0. Well, we did it, folks. That's the value of the limit. And this does simplify to, well, 0 over 1 if you took additional steps, which means it's exactly 0. So that tells us, that this rational function would have y equals 0 as a horizontal asymptote. It's getting really close to the x-axis as x goes off to positive infinity on this particular problem. We did it, folks. Part C looks nasty, but really it's the same exact process with a little bit more work simplifying right here. Any questions at all, folks, on finishing off that part C? Okay, so that's 2 problems down so far. Let's see what else weird problem we might have inside here. Part D definitely looks different on this one. But the same process still works just like before. We look only to the denominator for every one of these kinds of problems. Look for the term that matters the most, the one where if x grows larger and larger, it's going to be the one that is the most influential. And that would be the one with the highest power, so x squared this time. That indicates we should divide everything by x squared. Let me kind of highlight it this way. So first step, definitely write down the limit as x goes to negative infinity, divide everything by x squared. Now, let me know how this works out for you. If you're dividing 2x to the power 4 by x squared, you would get x squared, and 7 over x squared right here. So if you decide to simplify as you go, you'd probably write in your work like that. Let me know if this makes sense. Is this all right to folks so far? Okay, let's do it again. Down below, we're dividing that x squared by x squared, so we would get a 1. Divide 7x by x squared, and we'll get plus 7 over just x. So if you did try to skip a step, that's a pretty good one to skip. Writing out this is if you want to be really careful, write into the division by x cubes on them, and then it's much easier to simplify and be sure you got the right thing. But if you feel confident that you got it just by dividing and simplifying in one shot, that is okay when you're working out, say, quizzes on exams. Next thing we do is, after the division process, we look to property 8 for the limit laws, which essentially says anything with x in the denominator with a positive power is going to go to 0. Nothing happens to that one. That one's in a numerator, but 7 over x squared, as the denominator increases, that goes to 0 rapidly. And 7 over x goes to 0 as well, as x gets larger and larger. X squared, however, does not go to 0. As x goes to negative infinity, anyone see what would happen to the x squared right here?
I have a question.
Yeah, go ahead.
Where did the 2 go in the first term?
Oh, that is a really good question. I think I just forgot to write that one in.
Oh,
Thanks for
okay.
spotting. Yeah, there should be a 2 right here. You know, that's the value of taking this step, writing it all in. Easy to miss a little things if you're doing multiple things at once. Thanks again for spotting that, Iridia. Other questions so far? Okay, so watch out for that too. I have it highlighted here for that omission I made there. Next, x squared is still alive. And one thing you could do is, well, just imagine what does x squared look like? As a function, x squared goes like this. Notice the directionality on x. We're heading towards negative infinity on this one, but it really doesn't matter because the power is 2. If you're heading towards negative infinity, you're going up towards positive infinity. And same if you're going towards the right on this one. So the fact that it says you're heading towards negative infinity just means you're going this way. But the function values are just getting larger and larger and larger. The limit on this one does not exist. There's a couple ways to write down your answers. If you write out your answer like this, does not exist, I would find that completely acceptable. Or you could say that it's equal to infinity as well. That's what's happening, is it's moving completely upwards. And on the WebAssign system, notice that it says if an answer does not exist, enter in DNE. You can almost tell right away when they don't exist because the power in the numerator was higher than the power in the denominator. There is no horizontal asymptote, so we have no reason to expect the limit to actually exist on this one. And that's another indicator. This wasn't in a denominator when we did our division method. So here's where you put D does not exist, or if you like to paraphrase, DNE for does not exist. On paper, if you told me it equals infinity, I would also accept that. But this is more what WebAssign's wanting right here. Well, any questions at all, folks, on concluding part B?
I have a quick one.
Yeah, go ahead.
So, if this equation did have an asymptote, would that mean it would have an answer and it wouldn't be does not exist?
Absolutely right. Yeah. So
Okay.
that's this little weird theorem right here. It seems kind of innocuous at first, but it's exactly like you're saying. If you have a horizontal asymptote, your limit will exist. You'll be able to put in an actual value right there. But if we couldn't put in a value, like if we were to put in infinity or something, that means this asymptote did not actually truly exist in the first place. Well, does that answer your question there about that?
Yes, thank you.
Yep, you betcha. Thanks for asking it. Other questions or comments so far, folks? Okay, since this is just the first assignment, the very first section, I'm looking at the web assignments we're solving these just to give some extra hints and advice when you're going through the system. And the problem that we just worked out was very similar to this one. There's other weird things like, say, this one. There's no denominator on here. It'd be another kind of same issue. This doesn't have a limit that exists either. But some of them do, and this one looks pretty crazy. This one's a word problem. So we'll do one similar to this one as well. Well, let's see what else we have on the table. We went through our major limits. I want to include just one additional theorem that's going to help us with the word problems that are coming up. It's nothing major, just one application towards the end of the notes.
Before you go on, can I ask another question?
Yeah, absolutely. Go ahead.
If they don't have a denominator, why wouldn't they have a limit?
One way to think about it is the reason the limit exists is because the denominator is getting so large, the whole fraction is either heading towards zero or heading towards just a number. So say, for example, just some quick little different problems along those lines. If we had a function that goes f of x equals 2x power 4 plus 7, or 8, I put in an 8 instead. Now let's make it be x power 6 plus 1. With that x power 6 right there, let me zoom in just a little bit more. This is such a large term that the limit would go to 0. We put this down to a tie, now power 4. The limit on this one is going to be a 2. It has a horizontal asymptote getting closer and closer to 2 now. That's just because there's a balance between the numerator and the denominator. But the moment you wipe out the denominator, say entirely, this is what our function looks like now. It's just going to grow without bound in both directions. This one heads off to positive infinity. Does that make sense about that question there?
Yes, thank you.
You betcha. So anything that looks, say, like 5x plus 3, this one has a limit as x goes to infinity of infinity. If it was negative 5x plus 4 or plus 3, now as x goes to infinity, this one's dropping down towards negative infinity. And you can make a lot of interesting other problems, like, say, square root x squared plus 5x. Well, there's no denominator here to control what's happening in the numerator. So this one's also shooting off towards positive infinity in this way. So you need a denominator to control the growth of the function and actually have a limit that exists. Divided by x, there's a domain issue here for sure, but it looks like this one would have a limit all of a sudden. So those are the weird and wild things that can happen with limits. But for all of our limits we're looking at specifically, we're either going to positive infinity or negative infinity like we saw in this one. We're going to see what happens if we take the limit as x goes to 5 or 2 or something like that. So local behavior next in the next section. But any other questions, folks, so far about any one of these limits? Okay, well, let's go off to the last concepts for this section here. We have two exponential functions that we want to take a look at. Let me just space these out a little bit more. One of them is e to the x, and the claim is as you go towards negative infinity, the limit here is 0. Now that means the exponential function must have a horizontal asymptote, and it turns out it's true. But change the exponent, and change the direction on x, go to positive infinity, this one's 0 too, and it's not clear what exactly is going on here. So before we take a look at example 3, and this example is meant to be an application like the one in the homework, let's do some analysis here and see just what's going on with both of those limits. So we have two functions, e to the x and e to the negative x. Let's do some really simple plots on both of them. But whichever function we're plotting, they both have this asymptote. Y equals 0 goes here. It's overlapping the x-axis, so I'm drawing it kind of this way. Those zeros are what's matching with the zeros on the limits here and here. And now let's plot the functions. This one's the base e exponential function. Intersects exactly at 1. And it grows exponentially really, really rapidly. But if you move to the left from the y-axis, it decays exponentially towards the horizontal asymptote. It will never actually hit 0. E to the x is always positive no matter what. But you can get as close to 0 as you'd like by letting x, oh, I'm highlighting the wrong thing, by letting x go far and far to the left. You can get closer and closer by getting further and further to the left, heading off in that direction. So that's what happens to this limit. And the negative x here just causes a reflection about the y-axis. This one plots in this way. We'll put in a 1 here, reflects across the y-axis, and this is the new graph. Because we're heading towards positive infinity, we do have a limit of 0, because now we're going in this direction, towards the right, and the curve is getting closer and closer to a height of 0 in that towards the right direction. So what was special about here is not just that this is e to the x and e negative x, it's just as important that you're heading towards positive infinity. Well, let me try again. It's just as important that you're heading towards negative infinity on that one and positive infinity on that one. So all these symbols and decorations on the limit structure matter quite a lot. That's what makes calculus tricky to jump in. There's lots of notation, and we have to be very, very picky and specific with it to know just exactly what we're meaning. Well, any questions at all, folks, with these two graphs before we give this a try? Okay, let's go for this. We're going to next find the limit of this crazy thing right here. Now, the limit laws tell us the numerator is a constant, so it's going to just stay as a 17. We have a constant here, but the limit of 8 as x tends towards negative infinity is still 8. The thing that is affected by the limit is right there, e to the 5x. Well, e to the 5x seems kind of strange in a way because we're not dealing with e to the x. But that's okay, e to the 5x looks just like this. It just increases faster in this direction. So we can write out that this is limit as x tends towards, going to negative infinity on this one, of 17, 8 minus e to the, oh, I realize I'm just copying the problem. Sorry about that. I want to make one small change, and I forgot to do that. I want to write this in as 17 divided by 8 minus the limit as x tends towards negative infinity of e to the 5x. Let's write that 5x in a way that makes it look like an exponent. There we go, 5x. So I just did a bunch of limit laws right here, but that's the purpose of the limit laws, to know when you can take them for granted, what algebraic steps are really allowed. Let me highlight what those laws were. I'm going to scroll for just a moment and come right back. It's good to know what limit laws we used and what we can take for granted. The first thing we observed is dealing with a fraction, so I used this limit law right here. But when I went to the numerator, I observed it's a constant. That's limit law 4. I just left it as a 17. No reason to put a limit in front of that if it just turns into a 17. Then we are really taking the limit of the entire denominator, not just one term at a time. The limit law 2 says, well, you can do one term at a time. There's no harm there. So we use that up. Limit of this one is still 8. So we settled right down here, limit of e to the 5x. Now the limit of this one needs to be resolved by the formula right above. But before we go to work that out, does that make sense to folks on how we use those limit laws so far? Okay, again, in essence, this is all that's really happening so far with the limit laws. That limit structure went here and no change, we got a 17. It went here, no change, we got an 8, and it distributed here, and that's where we have to work something out, the limit of e to the 5x. So let's settle this one down and get an answer. You know, that's kind of a tricky limit, and I think it's worthwhile to take one little extra time on this. I'm going to put it in orange just to emphasize you don't have to work this out every time you do this problem. But if you want to use this formula exactly the way it's specified, you can say e to the 5x is no different than e to the x to the power of 5 using exponent laws. In that configuration, exponents just multiply, so it takes x times 5, written in as a 5x. Here's how that's helpful for us next. The limit, as x tends towards negative infinity, of e to the 5x is now equal to the limit as x tends towards negative infinity of e to the x to power 5, and we can work with that. There's a limit law for this as well. Let's find the limit law and use it. Let me reset the highlighting here. We can use limit law number 7. You might have noticed we haven't used that one yet, but what limit law number 7 says is, if you have an outer exponent, some power p, that's what we have right here, it's the 5, then the limit can go inside the exponent, and it essentially is saying the limit of e to the x to the power 5 is the limit of e to the x here, all then raised to power 5. So let's write that out as, now it is power 5 going out here. So that's this power that we wrote out. You know, let's use a bracket just to match up the notation. Ln x goes to negative infinity is right here. And now it's just affecting e to the x. That's the f of x function we see here. But once we get to here, this formula kicks in. That limit is just 0 because we're heading to negative infinity. So we're looking at 0 to the power 5, 0 to a 5th power is still just 0. Anything in orange, again, think of that as just extra to the notes, not something you have to do every time. But what all of this is saying is that limit is 0. A lot of work to just get to that spot, but you can take that for granted. So right here, we're going to get 17, 8 minus 0, and so the whole thing is just 17/8. This function has a horizontal asymptote at value 17/8, in other words. Any questions at all, folks, on running through this one?
Just one. Why didn't we divide by anything in the beginning?
Oh, good question on this one. So the reason we didn't divide by anything was this function right here is a little bit different than the other functions. Notice that the actual value of x, it's up here as an exponent. That means the strategy that we used above here is a little bit different. We want our x's to not be exponents. They should be down below as a base. The powers should just be constants for these kinds of functions. The moment we went from these functions, these are like the polynomial ones, to these, the exponential functions, it suddenly caused a shift in our strategy. We need to use this idea to get through the problem. So in other words, the reason we didn't divide by anything was because this was an exponential function and x was not a base, it was a power this time. Does that make sense about that question there?
Yes, thank you.
You betcha. I think that was a really good question. We should put that into the notes just to specify. We did not divide because y equals e to the 5x. There's a problem right there, that x is exponential. And all the other functions we were looking at, those were truly rational functions, a polynomial on the top, a polynomial on the bottom. What that meant was x was never an exponent. If x becomes an exponent, we need to use this theorem here as our new strategy. And really the major reason we're taking a look at this theorem is we ought to do at least one application after doing all of this limit work. We should say, what is it good for? And that's going to be our next problem. But first, as before, I do say this a lot, and if I forget to say it, never rude to interject. Any questions at the moment before we go to the next?
Yeah, really quickly. So why is it that we make the limit of e to the 5x right at the very beginning?
Right here?
Yeah.
Gotcha. The major reason for that was these portions right here being constants mean they were unaffected by the limit as x tends towards negative infinity. We were looking at limit law 4 right there. So if it's just a constant, then we center our limit around the thing that actually varied, the thing that involved the variable x itself. So all of our work is really resolve that. And limit law 4 says constants can be just left right in those positions. Does that make sense for that question there?
Yeah, that makes sense. Thank you.
Yep, you betcha. Thanks for asking that. Other questions or comments so far, folks? Okay. Well, the idea of this whole problem right here was if it's e to the x and you're going to negative infinity, you get a limit of 0. But we kind of extended on that idea. If it's e to the 5x, if it's e to the 12x, same deal. Only thing that could change that is if you have a negative in there. So if this was a negative 5x, whole process falls on its face. It's a different answer. So if you have a negative x here, you'll get a value 0 if you're going to positive infinity. And if it was, say, limit as x goes to infinity of e to the negative 12x, by our work that we did down here, there's no change. You're still going to get a 0. It's the fact that there's a negative that you're getting a 0 altogether, not as much the coefficient, in other words. So that's the formulas here. They extend in these weird ways to where you can have a 5x instead of an e to the x, or a negative 12x instead of a negative x here. Now we can put all that together for our application of the night. I try to put an application on all of my lecture notes, but I don't always assign a lecture, or excuse me, I don't always assign an application WebAssign. If there is an application of WebAssign, I make it a point to make sure we do one and solve it just to help out the homework. But if there's not an application WebAssign, think of the application at the end of the notes as just a point of curiosity, something you might find interesting that applies in that problem. We may or may not solve it. If we skip it, you can always ask me, hey, I'm interested in that. Can we take another look? I'll always be happy to go back to those applications. But this one is similar to the homework, so let's give this a try next. It says the Pacific halibut fishery has been modeled by this equation. And halibut is wonderful if you haven't experienced it, so this is an important problem already. So the halibut fishery, they're trying to maintain the health of these fisheries. So they came up with this model to say, well, what is it? B of t is the biomass in kilograms of time t. So the biomass of the halibut in your fishery, and what is t? Oh, geez, I was hoping for something like months or years or something like that. Looks like unit is unspecified on that thing, but we'll do the best we can with the unspecified unit. So at time t, this is how much biomass of halibut that you can put on the market in your fishery. What you wouldn't want to have is your biomass as a function looking like this, right? That's not going to be healthy. You're going to go out of business. And you wouldn't want the biomass function B of t to look like this either. You're going to run out of infrastructure. That's going to be terrible at the same time. You're going to have to do something to make sure you're selling off the fish fast enough to not accumulate all that biomass. Probably what you want is, here's your startup, and the biomass hits some kind of level where it levels off and you can deal with all that product. That's our hope of hopes. But I'm not sure what's going to happen with this function. And so that's what they're asking us right here. What is the limit as time increases without bound as t goes to infinity for this biomass? We hope it doesn't go to 0. That's not good for us. And we don't want infinity either. This limit had better exist. If it doesn't exist, they better come up with a better model for us. So we'll start by writing down to answer this question here. We need the limit as time this time goes to infinity. It's 8, 10 to the power 7. We're dealing with biomass, so scientific notation probably shouldn't be too unusual. 1 plus 3 e to the negative 0.7 t. So that's our limit to take. Really, I didn't do much here, but write in the problem and put in, instead of b of t, the actual function right here. Now, we have an exponential function, so we can't divide by anything to resolve it. Instead, we look at this part. It has a negative. Yeah, that would be all right. Let's highlight the whole function there. It has a negative, and t is also heading towards positive infinity. So if we look up, let's take a really quick peek. We should be in this case. There's a negative coefficient. We're heading to positive infinity. The limit of that function should just be a 0 altogether. Now, in example 3, we took an additional step to place the limit operator right here, but that's because we're learning the limit laws and what we can and can't do with it. When you get fluent with the limit laws, you'll start to take them for granted, but that's the goal, to be fluent enough with all these limit laws that you don't have to look at and cite them. You'll know that they're just working in the background for you. In this problem, here's what would happen. In one step, this is a constant, we'll ignore it. That's a constant, so it's ignored. And this is a constant multiplying. You know what? I think that's a new limit law. Let's indicate what's going on with that one, just to be sure. I don't think we've taken a look at this limit law, where it's a constant times a function. There should be something there for us. And that's limit law 3. It says it's okay if there's a constant times your function. Move it to the outside, and you're just taking the limit of the function. So everything highlighted in green is what the limit operator is going to influence. Just that one spot. All these other constants stay where they are at, and this one goes to 0 in the limit. So let's calculate the limits right here and now. We're going to get 8, 10 to the power 7, 1 plus 3 times 0 right here. And we didn't take any additional steps to put the limit operator right here. But again, that's because we're going towards our goal of taking the limit laws for granted and just observing it's influencing only this one spot. We got a 0, we just have to simplify our result. Any questions, folks, to that stage? Okay, let's simplify our result. We have 8, 10 to the power 7, divide by just 1. You know, if we're dividing by 1, let's just leave it like that. The 3 gets wiped out, and so this is how much we have. And we do have a unit for biomass, so let's say kilograms of halibut. Biomass. That doesn't look so bad, so this tells us whatever they're doing with the fishery, if the fishery operates in the same way, if the model is accurate, then this is going to give us an idea of how much revenue to expect each and every time we decide to cull the herd. And let's say that better, each and every time we try to get some revenue from this process of the fishery, we'll know that it's settling down to about this level to have a reasonable expectations of profits. Well, that's kind of what this is about. It's saying, what's the significance of this limit? So for this portion of the problem, we have to keep in mind we're going off to infinity. And so we can say, as time increases, you know, it's okay to say it that way, as time increases without bound, but it might be said a slightly different way. in the long run, if you're talking to a bank trying to get a business loan for your fishery, you'd probably say it in these terms. In the long run, the amount of biomass settles to around 8 times 10 to the power of 7 kilograms. So that's our interpretation of what happened here after we calculated the limit. So that's a value of taking a limit as time goes off to infinity. We're just looking at what is the behavior of a process in the long run. Or it could just be a random function, but occasionally looking at models is a great use for applications of calculus. What we did, folks, those are the kind of questions that you're going to see on the WebAssign homework. This is also the end of the notes. So essentially what happens here is I'll save them, convert it to a PDF, upload it to the Moodle website. And on the Moodle website, you'll also notice a couple changes. I'll put here a due date. It'll say due January 17th, because it's always going to be a 1-week turnaround from the moment we finish the assignment to the due date itself. I have the due dates already put in, but if we take extra time, I just push the due dates forward as needed. So I'll upload the solutions here. And now we're on section 2.3, limits of functions at finite numbers. That's a whole new topic, so I don't want to get too far in, but it might be a good idea to compare what we did so far in 2.2 to what we're about to do. So let's take a quick preview before we call it a night. First, any questions at all, folks, with the conclusion of these notes? Yeah, go ahead, Andrew.
Yeah, so with that last question that, okay, so as we go out to infinity, it's, you know, the level of biomass is settling. So is that like just that you have like a self-limiting population of halibut, or is it like you said that you're going in and like you're controlling that and the numbers in there have something to do with like how much you're taking or something like that?
Yeah, so I think for this particular model, I think this one is called the logistic model. So I feel like I might have misspoke when I thought they're taking biomass out at the same time. This is more the population is just going to settle without any changes. So we're not going to try to cull the herd. There's no predators, which would really be us. This is just the population of the halibut itself reproducing and dying off in the long run. So the logistic model isn't adding those extra effects of culling the herd, things like that, selling off the product. Does that make sense with that question there?
Yeah, that makes sense.
And now that you mention that, I think we can probably include that right here. It says in the long run, the amount of biomass settles around 8 times 10 to the power of 7 kilograms. And let's also say here, assuming, I'll put it in parentheses, assuming none of the fish are sold. So this logistic model is just saying what is going to happen to your population as a closed system, no predators. The format of this allows it to be not an exponential function that goes like this, growing without bound forever. It allows it to actually level off to some settling carrying capacity of the actual fishery itself. So thanks for asking that portion there. I definitely misspoke when I was thinking selling off part of the fish in the long run. This is all the fish just stay right there in the fishery. Other questions so far, folks, about that problem there? Okay, thanks for asking for that clarification on that, Andrew. I think that's the better thing to put in here for that answer on this one. Well, the purpose of these notes were really what is happening to a function in the long run, whether you're going far to the right. This would be more of an application. We're imagining time moving forward, for example. We can come up with applications as we're going towards the left, maybe not time, but maybe displacement, something going to the left of a starting point, some particle. We were interested in that long-term behavior. But the limits we never actually took were, what about the limits in the middle? What about the limit as x tends towards 0 or 1? We were only going towards the far left, negative infinity, or the far right, positive infinity for x. So now we're going to change this and start looking at what we might call local behavior. So that's the 2.3 notes. And now this is what it's going to look like. We want to take a limit as x tends towards a number specifically. So there's no positive infinity at all inside here. That means we're now working locally, actual values of the function itself. So those are going to be the kinds of things we take a look at next. And the idea with this, just as a preview, we'll come back to these notes and flesh out the ideas in much more detail. But if we were taking the limit as x tends towards 1, we have to say what the function is, so f of x. Here's what we imagine now this time. We're either going to be on the left side of the curve or on the right side of the curve. Either side we're on, we have to be heading towards the same overall height of this function. So if you come in from the right, the function is settling down at a height of around 2. But notice what I did not do. I did not put an input of 1. We're taking the limit as x goes to a, except possibly at a itself. We're taking x to be sufficiently close to a on either side of a. We are not setting x to a when we take this limit. This is a tricky limit in that certain sense, and that's why we did the end behavior type limits first before the local behavior. So what happens at 1 is irrelevant. That's really, really weird. That's why you're asked to compute f of 1. Oh, let me go back to this. F of 1 is definitely 1. That's just a function output from here to here. But if you're taking the limit as f of x tends towards 1, you're coming down in this direction, and in this direction, you're getting closer and closer to a height of 2. You are not getting closer and closer to a height of 1 exactly. That's pretty weird, and we'll take a look again at these ideas in a lot more detail when we come back 1 week from now after the holiday. But any questions at all, folks, about this preview so far? Okay, looks like we're ending just a little bit early today. But if you have any questions, don't hesitate to hang out. I'll be happy to help out. Otherwise, have a great holiday, folks, a great weekend. Drive safe, and I'll see you all when we come back on next Wednesday. Any last questions at all before we officially end class? Sorry, say again? Oh, sorry about that. We do have weekly quizzes, but I forgot to mention, I did want to give a quiz on the very first week since I didn't have too much to start out. So the weekly quizzes are going to start on the next week. Okay. Other questions at the moment?
So the next time we meet, we check that 2.2 done.
Yeah, you'll be in great shape once 2.2 is completed. Absolutely. Well, have a great night, folks. And I'll see you all on next Wednesday. Yeah, me too.
Thank you.
Yep, have a good one.